Welcome to this Prep for Uni. Online video on the Otto cycle, which illustrates the working of a petrol engine. The Otto cycle is the thermodynamic cycle that underpins how petrol engines function. We'll explore each stage of the cycle, observe how piston motion relates to pressure, volume changes, and gain insight into how combustion engines convert heat into mechanical work. The Otto cycle consists of four thermodynamic processes. Adiabatic compression, from point 1 to point 2. Heat addition at constant volume, from point 2 to point 3. Adiabatic expansion, from point 3 to point 4, and heat rejection at constant volume, from point 4 back to point 1. These steps form a closed loop that repeats many times per second in a running petrol engine. This pressure-volume diagram illustrates the Otto cycle, showing how pressure and volume change during each process. Each curve or vertical line represents one thermodynamic step. The area enclosed within the loop represents the net work done by the gas on the piston, the basis of mechanical power generation in the engine. We'll now walk through each step with diagrams showing piston motion inside the cylinder. The Otto cycle begins at state 1, where the piston is at bottom dead center, fully extended downward. The gas occupies its maximum volume and is at its lowest pressure. This marks the beginning of the compression stroke. The piston moves upward, compressing the gas without heat exchange. This is an adiabatic process. As the volume decreases, the gas pressure and temperature increase. The system moves from state 1 to state 2 along a compression curve on the PV diagram. At state 2, the piston reaches top dead center, its highest position. The gas now occupies its minimum volume, and its pressure and temperature are much higher than at the start. This is the end of the compression stroke. From state 2 to state 3, heat is rapidly added via combustion. The piston remains at top dead center, so the volume remains constant, while the pressure rises sharply, from P2 to P3. This represents an idealized constant volume heat addition. In real engines, especially rotary types, the piston may move slightly, but combustion occurs so quickly that the assumption holds reasonably well. At state 3, the gas reaches its maximum pressure and temperature. The piston is still at top dead center, and all the thermal energy from combustion is now stored in the compressed gas, ready to perform mechanical work in the next stage. This is the power stroke, the most important part of the cycle. The high-pressure gas expands, pushing the piston downward and doing mechanical work. This is again an adiabatic process, so the gas cools as it expands. The area under the expansion curve, 3 to 4, represents work done by the system. By contrast, the area under the compression curve, 1 to 2, represents work done on the system. The difference, the area enclosed by the loop, is the net mechanical output per cycle, shown in red. At state 4, the piston is once again at bottom dead center. The gas has expanded and cooled. The system now prepares to reject heat and return to its initial state. In the final step, from state 4 back to state 1, heat is removed from the system at constant volume. The piston remains stationary while the gas pressure drops. This resets the cycle, allowing it to repeat. The Otto cycle repeats rapidly inside a petrol engine cylinder, transforming heat from combustion into mechanical work that drives vehicles. Though idealized, this model helps engineers understand performance and efficiency limits of internal combustion engines. Thank you for watching. Visit Prep for Uni online to access free lessons, tutorials, and structured learning resources in science and engineering.